Hey, I'm back. It's me, your favorite professor, for another exciting episode of Geography 105 Physical Geography. It's week 14, episode 14, Groundwater. Live to you from the basement, but what we're going to do now is check out a little seen part of the underground bat cave. Come with me. Yes, it's the majesty and glory of the sump pump here in the lowest part of the basement. This is filling with water right now as we speak, and it fills with water almost continuously. And during certain times of the year, the sump pump goes off about every 8 minutes. Why is that? Now, I know what you're thinking. You're thinking $417 a credit hour, and I'm looking at this guy's sump pump. Watch what happens. And there it goes. Glorious, wasn't it? Yes, indeed. Now, what does that have to do with anything? Well, let's go outside and I'll show you something else.
Backyard Olympics.
Step 1. Compost leaping.
Woo, smooth. Step 2.
Tomato cage shot put. Or whatever.
Bingo!
One more try.
Oh, I thought, okay.
Well,
No,
I mean,
just cause.
oh,
1 point.
1 point. Alright. Now puddle run.
Woo! Gold medal!
So you saw all that water on the ground, and you saw the snow in the background, and it had just been raining possibly, and there's a whole bunch of water on the ground. So what? But before I do that, I have to tell you a little bit about the ground. Different day, slightly breezy, and here we are in my backyard. My backyard is not all the same level, and I am right now standing on the highest part. And I look out there, and the backyard actually gets lower this way. Let's see. All right, so here I am in the lowest part of the backyard. In that video you just saw, this is where all that standing water was. And this is where water accumulates. Now, underneath my feet right now, no matter where I'm standing, whether I'm in my backyard or on the street, if you dig enough, you'll find water in the ground. And of course, this is how a well works, because let's see, about 2/3 of you get your water at home from the city, but about 1/3 of you are using well water. So we have this thing called groundwater. Here's a cross section of a typical well. And what you see up here, all right, there's the surface of the ground, just like my yard. And as you go down into the ground, in this picture, the ground is dry. Well, this is the unsaturated zone. And as you dig your well deeper, you hit this water. So where that water is, that line is the water table. And it says water level, and in the well it's the water level, but that's the water table underground. You go down a little further, underneath the water table is the saturated zone. So in my yard, and in my neighborhood, in fact, in a big chunk of my neighborhood, the water table is not that far down. It is, in fact, that far down. And when it rains, or when there's a lot of snow melt real fast, and there's suddenly a whole lot more water than the ground can move, then we have groundwater seeping up to the surface. So here's a reasonable question. How can the ground be filled with water? Well, the ground is made of sediment, whether that's loose dirt or in the form of rocks. So sediment has been compacted into rocks, but when you look at it in a microscope, or sometimes you can see it with your eyes, sediment is composed of fine particles, little grains of minerals, of little bits of other rock, of organic material, but there are spaces between those particles. And that's a property called porosity. Now take a look at this. Here's a handy little diagram here. Now this shows you the difference between sediment grains where on the left over there isn't any space in between those grains. Towards the middle of this little diagram, there are some spaces in there. Now, when the ground is dry, those spaces are filled with air. But in the saturated zone, those pore spaces are filled with water. All right, and here's another word for you. Look at the bottom of this diagram, permeable. Permeability is the ability of sediment or rock to transmit water. So porosity is how many spaces are there between grains, how many holes, and permeability is how well can that rock or sediment, how well can water move through it. Funny thing about that water that's on the ground, that's not just water that had accumulated due to snow melting. That's actually groundwater. It's groundwater that has come up to the surface because there's so much of it. Which leads me to two more terms we got to know about. When water goes into the ground, like rain falls and water seeps into the ground, that's called recharge. And when you take water out of the ground, like a well, or if it just sort of flows out of the ground, that is called discharge. The word for a body of water in the ground is called an aquifer. So an aquifer can be recharged or an aquifer can be discharged. So I got an aquifer under my house. In fact, I got more than one. And here's a diagram from your textbook. You can see that there are 1, 2, 3 aquifers in layers with a lot of porosity. Now take a look over on the left here and you see that well. That well is drawing water from the top aquifer. We're going to call that an unconfined aquifer. I mean, there's nothing on top of it except the surface. Now go down one layer to here. This is a confined aquifer. It is between two bodies of rock that the water can't get through. That confining bed is low porosity and no permeability. There's no pore spaces and water can't go through it. All right, so this is a small scale aquifer, but I don't want you to get the sense that these things are tiny. Here is a big one. This is an aquifer that covers several states and actually a big chunk of the Midwest here, going from South Dakota to Texas. Texas is over here. The aquifer, the body of water, is inside a layer of rock or several layers of rock that have high porosity, and we have dug lots and lots of wells in there to water crops. Now this aquifer is steadily shrinking. All right, let's go back to this. When you discharge an aquifer, the water table drops down. And some of you know that if you use a well long enough, you have to dig it deeper because the unsaturated zone gets bigger and the saturated zone gets smaller as we empty out the pore spaces of water. That's what we're seeing all over the world, and particularly in this location in the Midwest here. And this is actually big trouble. Let me take you to Houston and tell you a story about that. All right, we're going to talk about a concept called subsidence. And let's define that real quick. So here we are in Houston, Texas. This is Galveston Bay here, and here's the city of Houston, and here's downtown. So Houston has experienced subsidence. Now let's define that real quick. Here's the definition. Subsidence is the sinking of the ground due to water being removed. And there actually can be all kinds of causes of subsidence, but here we're talking about this. Water that's in the pore spaces in the ground helps to hold up the ground. So you take out the water, you have these empty spaces now, the ground's going to compact together. Now here's a visual. Take a look at this guy. And let's zoom into the bottom here. The year is 1977. He is standing. That is the surface of the ground in 1977. Oh, let's zoom out a little bit here. 22 years before that, the surface of the ground was up here. And 30 years before that, the surface of the ground was there. This is farmland in California, and so much water had been pumped out of the ground to water these crops that the ground sank that much in 52 years. Astounding, isn't it? All right, let's come back to Houston. So you see these very light blue lines here. And what this is telling you, remember isobar maps? Remember when we looked at the atmospheric pressure and we drew the lines and everywhere along that line was a pressure line? Okay, these are subsidence lines. So everything on this outer line here sank about 0.2 of a foot. Okay, you're thinking not that much, but let's get down to downtown Houston. A little bit more. Let's see, 0.2 of a foot, 0.4 of a foot, 0.6, 0.8. So not quite a foot was the amount that Houston had been sinking from the period of 1906 to 1943. What was that coming from? Well, not just groundwater, but oil and gas removal too. So petroleum, liquid petroleum, can also help to hold up the ground. Take it out, you're going to get subsidence. All right, let's go to the next time period and check this out. All right, 1943 to 73. That's 30 years. And wow, what a difference. So Houston exploded in growth. It's now the 4th largest city in the United States. There's New York, LA, Chicago, and Houston. So many people using so much groundwater that what we're seeing, where that red arrow is subsidence rates 7 feet. The entire section of Houston, that part inside that 7-foot line, sank, subsided 7 feet. So for the next 20 years, Houston said, all right, we better do something about this, and we better throttle back the amount of groundwater we're pulling out of the ground here. And they did. So what we did see, we still see pretty high subsidence rates here, up to 4 feet, but they cut it almost in half. And how did they do that? Well, what they did was that they changed the way where they got their water from. Now take a look at this. 1976 up here, most of the water, about 2/3, they're pulling out of the ground. They're getting some from the Brazos River and some from the San Jacinto River. And if you look down at the bottom here, 1996, they cut their groundwater use by half to 1/3. They're still pulling water out of the Brazos and San Jacinto rivers, but now they're pulling it out of the Trinity River. All right, so look over here on the right. They're using acre feet. Well, let's see. 0.826 million acre feet in 1976, and in 1996 are using 1.016 million acre feet. What is an acre foot? Well, it's a way of measuring huge amounts of water. Here's an acre foot. All right, look at this football stadium, end zone to end zone. Just look at the gridiron. Okay, that's an acre. A football field is an acre. Now, imagine that football field flooded with 1 foot of water. That's 325,851 gallons. Okay, that's an acre foot. Now, go back to this. This is how much Houston is using, about 1 million. Now, that's 20 years ago, right? So, 25 years ago. All right, that's a lot of people. That's a lot of water. Well, let's do this now. Let's compare the usage in water from 2 cities in Texas. Far east side on Houston and far west side in El Paso. So look at the population differences here. Houston's 4 times as many people. And look at the use in acre feet. All right. Houston uses 3 times the water of El Paso. Sure, that's not surprising. This number over here, GPCD, that's gallons per person per year. So El Paso's people use a little bit more water than Houston's people. All right, well, let's look at the 2 cities. Okay, groundwater. Houston gets 35% of its water from the ground. El Paso's getting about 80% of its water from the ground. Now let's take a look at how they're using water in these 2 cities. Okay, El Paso. Municipal means people who turn on their faucets. Manufacturing. Mining. And wait a minute, what are they mining in Houston? Oh, they're mining salt. Yeah, they're mining salt. Okay. electric power generation, irrigating, and no surprise, El Paso's a desert, so it uses more for irrigation and more for livestock too. All right. That's the use of groundwater in two American urban settings. And that's where we're getting subsidence from. Now, we talked about subsidence in Houston, but interesting things happen in a desert when you start pulling water out of the ground. You get, not only you can get subsidence, but you can also get these things. These are ground fissures. Now take a look at this. This is just the soil in the desert, and it's split open. Here's a fissure. Here's another fissure. And these things, this is what happens when the ground dries up and it pulls apart. And how big can these things be? Well, these things can be pretty big. All right, here's an old trailer home. And here's a ground fissure. And here's another one, and here's another one. And this view was captured by a balloon that was holding a digital camera. And here's the view from the ground. I used to play in these things when I was a kid. It was fun to go out there and, fart around in these fissures, and I had no idea it was because we were pulling groundwater and causing these fissures. Well, there it is in text for you. All right, so that's a quick primer on groundwater. Underneath our feet in the ground, there is sediment and there's rocks and there's pore spaces, and those pore spaces are filled with water. When water goes into the ground, the water table rises, and when we take water out of the ground, the water table sinks. Underneath my house right now, the water table is up fairly high. In fact, it probably is, if you look around, there's a wall of my basement here. The water table actually is probably just about level with my head when I'm standing up in the basement. And when it rains, it's much higher, right? And that's why all of that water keeps flowing into my basement and keeps flowing into my sump pump area and has to get pumped out. So, do some reading and check this out. Why is there a screwdriver in the bottom of my sump pump? Oh, okay. Yeah. All right. Sure, whatever.